Bismillahirrahmanirrahim. I am Sadashri from Batch 7 and the topic of my presentation is Barium Titanate based piezoelectric sensors chemistry and its application in medical devices. In this topic, I will cover the introduction, piezoelectric effect and mechanism, barium titanate based chemistry, its fabrication and design, what are its application in medical devices, and its advantages and challenges. In the end, I will tell you about the future trends and development. Now, what is piezoelectricity? Piezoelectricity is the creation of electric charge in material under mechanical stress. In simple words, materials are physically deformed and they create electricity. For instance, imagine a piezoelectric crystal inside a cigarette lighter. When you press the button, you are applying the mechanical pressure to the crystal. This pressure causes the crystal to generate a small electric charge that triggers the sparkle and ignite the fuel. Now, piezoelectricity was first discovered in 1880 by the Curie brothers, who noted that an electric charge while compressing or bending the crystal such as quartz or topaz. The phenomena is named after the Greek term piezo, which means to press or to squeeze, and was a seminal discovery in the study of material science. Now, what is piezoelectric sensors? Piezoelectric sensors are the devices that use piezoelectric materials to detect changes in pressure, acceleration, temperature, and other environmental parameters. Barium titanate discovered in 1940s and it has many applications in medical devices. Now, what is the effect and mechanism of piezoelectricity? Its fundamental principle, piezoelectricity is the capacity of some material to generate an electric charge in response to exert mechanical tension. This phenomena is particularly frequent in crystalline crystals such as quartz and topaz. Crystal structure and polarization. The crystal structure is the foundation of piezoelectricity. In a structure of material, piezoelectric materials have asymmetrical crystal lattice unit cell, and they are result in an uneven charge distribution. When these materials are deformed, like stretched or compressed, the crystal symmetry is altered. We can say that its symmetry is changed and they result in the shift of internal distribution of electric charge. Now we will see that how electric charge generates. When a mechanical stress is applied to the piezoelectric, it causes changes centers to shift inside the material, and this distortion causes an imbalance in the distribution of positive and negative charges, and they result in the detectable electric potential. Now, what are direct and reverse piezoelectric effects? The direct effect is the generation of electric charge in response to mechanical stimulus, and that is the basic idea underlying piezoelectric sensor. Converse is the definitely opposite of that, and that is occurs when the piezoelectric materials become deformed, and this methodology is used in actuators and other devices. What are barium titanate based piezoelectric sensors? Piezoelectric sensors imply the direct piezoelectric effect to convert the mechanical energy into electrical energy. These sensors are often used in application including pressure sensors, accelerometers, and vibration sensors. The component of barium titanate based piezoelectric sensors include the piezoelectric substance, that is barium titanate based here, and the other is electrodes, the last one is housing. Now, what is the mechanism in barium titanate based piezoelectric sensors? Due to its excellent piezoelectric properties, the barium titanate is a common piezoelectric material for sensors equators, and capacitors. Barium titanate based piezoelectricity is due to its crystal structure, or how it responds to the mechanical stress, or how they create the electric charge. The structure of barium titanate consists of repeating unit cells which consist of barium ions and found at the unit cell corners. Titanium ions may be at the center of unit cell. The last one is the oxygen ion. They are found in the unit cell phase centers. The perovskite structures may change polarization in response to mechanical stress and make the barium titanate an exceptionally effective piezoelectric material. The key characteristics of barium titanate structures is that they have two phases. Like first one is cubic phase, that is also known as the high temperature phase, and the other one is teragonal phase, and it is also called the room temperature phase. The effect of piezoelectricity on piezoelectric properties. First of all, that is the spontaneous polarization, and the other is impact of mechanical stress. And then that is the piezoelectric effect. The direct piezoelectric effect is the creation of electric charge when mechanical forces are applied to barium titanate crystals. As the materials deforms, the dipoles within the crystal are moved, producing a measurable electric signal. And the indirect piezoelectric effects occur when an electric field is given to the crystal, inducing the mechanical deformation. This phenomena is necessary for equators, which employ the barium titanate to transform the electrical energy into mechanical motion. Then what are the piezoelectric properties in barium titanate based sensors? Barium titanate based is often used to modify the high piezoelectric coefficients, which influence the amount of charge generated for a given mechanical tension occurs. This renders the barium titanate based sensor to even minor deformations, making them appropriate for the diverse applications including pressure sensors, detect changes in pressure by sensing the change in electric charge, cause the deformation of barium titanate crystals. The important factors that affect the piezoelectricity are temperature, that is directly proportional to that is inversely proportional to the piezoelectricity. It means that when temperature is increased, the piezoelectric properties are decreased. And the other factor is electric field. Electric field is directly related to piezoelectricity, and doping is also directly related to piezoelectricity. It means that when piezoelectricity properties are increased, doping is also increased. And the microstructures and the grain size is inversely proportional to the piezoelectricity. It means that when we want to increase the piezoelectric properties, at that time we need to reduce the size. The fifth factor is mechanical stress, that is also directly related to piezoelectricity, and the last one is pooling, that is also directly related to the piezoelectricity. Now, sensor development and its prospect. Piezoelectricity is distinguished by the linear interaction of electric and mechanical field. When a material is exposed to mechanical stress, the piezoelectric effect, which is at the heart of this phenomena, generates an electric charge on its surface. The piezoelectric effect, which is used in here, first of all, the magnitude of produced charge is proportional to applied stress, and its polarity varies depending on whether the stress is compressive or tensile. Now, what is the methods that we use in synthesizing the barium titanate? The first method is soul cell method. What we'll do in this method is, first of all, we'll take the titanium 4 isopropyl and 2-propanol, and then glacial acetic acid is added. it becomes titanyl acylate, a precursor. After that, barium acetate solution of 1 molar quantity is added and it gives gelatin. Amorphous barium titanate gel is formed after calcination at 60 degrees Celsius or 80 or sometimes 1000 degrees Celsius, results in a crystalline fine powders that make the nanoparticle of barium titanate based particles. The other method is the preparation of synthesis sol. In this method, we take titanium 4 isopropoxide plus glacial acetic acid and it gives us the titanyl acylate precursor. After that, deionized water is added and they give us the hydrolyzed water soluble titanium precursors. After that, alkaline KOH solution 100 degrees Celsius temperature is given and barium titanate sodium of 1 molar solution is formed. Crystalline fine powders are formed, and the other method is hydrothermal methods, and here high temperature and high pressure is used, and solid state reaction technique is also used for preparation of nanoparticles of barium titanate. The crystal structure and phases of barium titanate. There are 4 phases of barium titanate: rhombohedral, orthorhombic, tetragonal, cubic, and hexagonal. The tetragonal structure with polar orientation is the best for piezoelectric application in composites. Barium titanate crystal structure is very temperature sensitive, with several structure phases appearing within the certain temperature range, including rhombohedral, orthorhombic, tetragonal, cubic, and hexagonal phases. Now, what is the crystal structure of barium titanate? Barium titanate has a perovskite crystal structure with a cubic unit cell containing barium ion at corner, titanium ions in the middle, and oxygen at the face-centered location. At ambient temperature, the barium titanate exhibits the tetragonal distortion. It results in the non-centrosymmetric crystal structure required for piezoelectricity. This distortion leads the titanium ion to move out from the center of unit cell and result in a net electric dipole moment. Barium titanate crystal structure is characterized by the space group, which implies tetragonal symmetry, and the Curie temperature of barium titanate is around 120 to 130 degrees Celsius, above which the material becomes paraelectric and lose its piezoelectric characteristics. So we can say that Curie temperature is a crucial metric in deciding if barium titanate is suitable for certain application or it is not suitable for that. So we can say that barium titanate has a high electromechanical coupling coefficient, and it indicates the effectiveness of energy transfer between the mechanical and electrical forms. After that, uh, crystal structure has a substantial effect on the microstructure, which in turn impact the electrical and mechanical stress. Larger crystal size may boost the piezoelectric response by decreasing the surface to volume ratio, and a more uniform distribution of stress over the crystal is leads to the high performance in application like a sensor or actuators. What is doping and its modifications? What is doping and its modification? Because of the versatility of the barium titanate and earth metal perovskite structure, researchers outline usually the dopants, and what is actually doping. Doping in material refers to the intentional addition of small amount of other element like dopants to a material, barium titanate, to alter its properties. This can improve its piezoelectric performance, electrical conductivity, and other characteristics. And doping site, the phrase doping site refers to the specific location inside a crystal lattice that can be occupied by the atom or molecule such as dopants. What is the modification? Modification means changing or enhancing the material's properties, usually the physical properties of the material, such as changing its shape, structure, or composition to improve its performance in sensor or other applications. Uh, just look at the diagram here. We have three colors. The one is green, that is for the first doping site. The other is blue, that is for the other doping site. And the last doping site is represented here in the pink color and is shown by the term O. So here we have different doping sites where we can add the dopants to enhance its piezoelectric properties. What is the design of a piezoelectric sensor? In ancient time, its design seems like that way. The sensor core is made up of piezoelectric material, which is often quartz or ceramic. When the mechanically deformed, this material produced an electric charge, and in classical vibration sensors, a spring suspends a mass, allowing it to move in reaction to vibration. So here we have the mass and a spring is attached to that. So a piezoelectric sensor replaces the spring with a piezoelectric device that supports the mass. When a vibratory movement or mechanical pressure is given to the piezoelectric sensor, the piezoelectric materials deforms. Now, what is the manufacturing of piezoelectric device? To manufacture high quality piezoelectric devices such as energy harvesters, wearable technologies, and all aspects of the process, including material synthesis, piezoelectric film production methods, and application requirement, they must be considered. Some of the variables that have a significant influence on the performance of piezoelectric system, it includes the nanoparticle size, its properties, nanoparticle addition to the polymer matrix, and applied force and frequencies. A barium titanate piezoelectric sensor is built in the multiple process to transform the mechanical stress into electrical signals. So now we'll see that what are its applications in piezoelectric sensors in medical devices. So this diagram shows that the piezoelectric sensors are used in many different applications like in cardiac pacemakers, body fluids detection, or in cell culture, or in many other fields. First of all we have the organ transplant, the other is the wearable devices, and the neurological parameters. First of all we'll see its applications like defect of bone repairing, the other is anti-cancer, and after that its application in implantable biomedical devices and many more. Now we'll see that what are its applications in anti-cancer devices. While breakthrough in cancer therapy have typically resulted in high survival rates and fewer cancer deaths, trends differ by area and disease type. For example, in China, the age standardized cancer death rate has declined overall, but the incident and mortality rates for the certain malignancies such as colon, rectum, prostate have grown dramatically. Surgery, radiations, chemotherapy, immunotherapy are the examples of current therapeutical modalities. Now we'll see that the mechanism of piezoelectric nanodrugs is activated by the ultrasounds for cancer therapy and can be divided into two types. The first one is direct piezoelectric effect, which generates the signals to act on the cell, promoting the cancer cell apoptosis, generating the ROS through piezoelectric catalyzing intracellular oxidation reduction, which directly eliminate the cancer cells. In addition to research state that the piezoelectric effect can be used with other therapies such as chemotherapy, radiation therapy, photodynamic, and other. The lack of lymphatic veins with tumor tissues cause the fluid retention between the tissues, resulting in the black pressure, or between the tumor tissues and blood arteries. This prevents the medication penetration into deep tumor tissues, resulting in tumor recurrence and metastasis. Now this diagram shows the how nanodrug release the particles and application in implantable biomedical devices. In recent years, the area of medical therapy has been tremendously advances in implantable devices, providing a fresh hope to the patient facing a variety of health difficulties. These gadgets have the potential to dramatically improve the quality of life for those in need. However, these implanted technologies have advanced a major concern in that field and the necessity for a dependable and long lasting power supply. To solve this issue, researchers have been looking at self powered solutions with the goal of giving implanted devices the capacity to sustain themselves for lengthy periods of time. Several promising technologies such as piezoelectricity, thermoelectricity, pyroelectricity, and triboelectricity and their hybrids have emerged as a potential energy source for application ranging from energy harvesting and environmental disinfection to enable self-powering capabilities in power detection and implantable devices. Now, its other application is in biomedical imaging. Barium titanate based piezoelectric sensors have found widespread usage in biomedical imaging applications, notably ultrasounds and photoacoustic imaging. These sensors can transform mechanical energy into electrical energy, making them useful for sensitivity and sensing variety of physiological factors. In ultrasonic imaging, barium titanate based piezoelectric sensors detect echo of high frequency sound waves reflected by inside organs and tissues. These electrical impulses generated by the sensor are then analyzed to provide the high resolution photographs of the body's interior architecture, and barium titanate based piezoelectric sensor provide the various benefits in ultrasound imaging, including excellent sensitivity and its resolution, a wide bandwidth and frequency range, a high signal to noise ratio, and a small and lightweight construction. Now, what is photoacoustic imaging? Photoacoustic imaging is another biomedical imaging technique that uses the barium titanate based piezoelectric sensors. In this technology, the sensors measure the acoustic waves produced by the tissue absorption of laser light. This enables high resolution imaging of tissue and organ and have been employed for a variety of purposes, including cancer diagnostics, ratio and tissue engineering, and a small and lightweight construction. The use of barium titanate based piezoelectric sensor in biomedical imaging has many advantages. It includes high image resolution, greater sensitivity, shorter scan duration. Furthermore, the sensors can measure a variety of physiological characteristics such as blood flow, tissue elasticity, and molecular biomarkers. Future research possibilities include developing implantable sensors, integrating these sensors with the other biomedical devices, or seeing machines learn the methods to improve the sensor performance. Now, what are ultrasonic transducers? The essential component of an ultrasonic transducer is barium titanate based piezoelectric sensor, which convert the electrical input into acoustic waves. When an electrical signal is delivered to the sensor, the piezoelectric material expands and contracts, resulting in the sonic waves. These waves are subsequently transferred into the body, where they interact with the internal organs and tissues, resulting in echoes measured by the sensor. These discovered echoes are then translated back into the electrical signal and then proceed to provide the high resolution photographs of body's interior architecture. Barium titanate based piezoelectric sensors provide various benefits in ultrasonic transducers, and the great sensitivity of barium titanate based piezoelectric sensors, it allows for detection of faint echoes and resulting in high resolution imaging of microscopic structures and tissues. These sensors broad bandwidth permits the transmission and detection of wide range of acoustic frequencies, allowing and enabling the high resolution imaging of various tissues and organs. The high signal-to-noise ratio of barium titanate-based piezoelectric sensor allow for detection of faint echoes even in the presence of background noise, enabling for a high-resolution imaging in noisy condition. Overall, barium titanate-based piezoelectric sensors serve an important function, and ultrasound transducers provide high-resolution imaging of interior organs and tissues. In addition to their superior performance, barium titanate piezoelectric sensors provide various practical benefits in ultrasonic transducer. They are small and light, making them easy to include into ultrasonic probes and transducer. They are also quite affordable, making them an economical choice for ultrasonic imaging application. Now, what are its use in blood pressure? The barium titanate based piezoelectric sensors are widely employed in medical device industry. Notably, in blood pressure monitors, these sensors are crucial for detecting blood pressure, which is a vital marker of cardiovascular health. Blood pressure sensors are an important part of medical equipment like sphenometers, which are used to diagnose and monitor the hypertension, heart diseases, and other cardiovascular disorders. The piezoelectric effect, or the capacity of certain materials to create an electric charge in response to mechanical stress. The operation of barium titanate based piezoelectric sensors pressure in computers. Blood pressure exerts mechanical force on the barium titanate based piezoelectric sensor, causing it to create an electric charge, and an electric charge is then measured and translated into a digital signal, and that is shown on the medical equipment. Barium titanate based piezoelectric blood pressure sensors has various benefits over typical blood pressure sensors. These benefits include excellent precision, sensitivity, small design, low power usage, and these sensors' excellent precision and sensitivity allow them to give the consistent and exact blood pressure measures even in individuals with complicated cardiovascular disease. These sensors' tiny size makes them easier to integrate into medical equipment. Their low power consumption allow them to employed in a battery powered devices. Now, what is its application in respiration rate sensor? Barium titanate based piezoelectric sensors are widely employed in medical device industry, notably in respiration rate sensors. These sensors are crucial in detecting respiratory rate, which is a vital indicator indicating the health of respiratory systems. Respiratory rate sensors are an important component of medical equipment like ventilators, which helps patients with respiratory difficulties, and piezoelectric effect, which allows the certain materials to create an electric charge in reaction to mechanical stress, and it lies at the heart of barium titanate based piezoelectric respiration and rate is piezoelectric respirations to reduce are to produce the electric charge. The electric charge is then measured and translated into the digital signal that is shown on the medical equipment. Barium titanate based piezoelectric respiratory rate sensors have various benefits over standard respiratory sensors. These benefits include excellent precision, sensitivity, small design, and lower power usage. These sensor excellent precision and sensitivity allows them to give the consistent and exact respiration rate data, especially in patients with complicated respiratory diseases. The sensors' tiny size makes them easy in patients with the complicated respiratory disease, and their lower power consumption allows them to employed in battery powered devices. The use of barium titanate based piezoelectric respiratory rate sensors is broad and extensive. These sensors are utilized in a wide range of medical devices, including ventilators, respiratory monitors, and the portable medical equipment. They are utilized in therapeutic settings such as hospitals and clinics to monitor the patients with respiratory illness. Further, these sensors are employed in research settings to investigate the respiratory system and create new respiratory illness therapies. Now, what are pacemakers? Pacemakers are medical devices that are implanted in the body to control the heartbeat. Barium titanate based piezoelectric sensors are often utilized in medical device production, especially in patients with irregular heart rhythms. Barium titanate based piezoelectric sensors are crucial in pacemakers because they detect the heart rate, heartbeats, and regulate the pacing. Barium titanate based piezoelectric sensor in pacemaker works on the piezoelectric effect with the ability of certain materials to create an electric charge in mechanical stress reaction. Pacemakers employ mechanical force from the heart rate to create an electric charge in barium titanate based piezoelectric sensor. This electric charge is then monitored and utilized to control pacemaker rate of operation. Barium titanate based piezoelectric sensor provide various advantages in pacemakers, including high sensitivity, precision, small design, and because of their greater sensitivity, these sensors can detect even light variation in the heartbeat, allowing for accurate pacing modulations. The excellent precision of these sensors guarantees that the piezoelectric pacemakers work properly, even in individuals with complicated cardiac problems. The sensor's tiny size allows them to easily integrate into the pacemakers, which are generally small devices implanted in the body. The use of barium titanate based piezoelectric sensors in pacemaker provides the various benefits to patients. These advantages include greater heart function, less symptoms of heart failure, and a higher quality of life. Furthermore, barium titanate based piezoelectric sensors can assist to lower the likelihood of problems from pacemaker placement, such as infection and bleeding. Now, what are implantable cardiovascular or cardioverter defibrillators? Barium titanate based piezoelectric sensors are often employed in medical device manufacturing, notably in implantable cardioverter defibrillators. ICDs are medical devices implanted in the body to detect and create irregular cardiac beats like arrhythmias. Barium titanate based piezoelectric sensors are crucial in ICDs because they detect the aberrant cardiac rhythm and initiate the administration of electrical shocks to restore the normal heartbeat. The piezoelectric effect, which allows the satin material to create an electric charge in response to mechanical stress, underpins the operation of barium titanate based sensor in ICDs. In case of ICDs, the mechanical stress is imposed by the hot bed, causing the barium titanate based piezoelectric sensor to produce an electric charge, and the ICDs then measure and analyze the electric charge to detect the aberrant cardiac rhythms. Barium titanate based piezoelectric sensors provide various benefits in ICDs. It includes the high sensitivity, high precision, and a compact design. These sensors has great sensitivities, allows them to detect and even little variations in the heartbeat, enabling for the accurate identification of aberrant cardiac rhythms. And the excellent precision of the sensors guarantees that ICDs work properly even in individuals with complicated heart cardiac problems. And now, what are its uses? The uses of barium titanate based piezoelectric sensor in ICDs provide various benefits. The advantages include enhanced heart function, lower risk of sudden cardiac deaths, and the higher quality of life. Furthermore, a barium titanate based piezoelectric sensors can assist to lower the risk of problems related to ICD implantation, including the infection and bleeding. What are neurotransmitters? Barium titanate based piezoelectric sensors are widely utilized in medical device production, notably for neurotransmitters. Neurostimulators are medical devices that helps and create the neurological illness, including Parkinson's disease or epilepsy and chronic pain. The device functions by sending the electrical impulses to the particular part of the brain or nervous system. Therefore, they regulate the aberrant brain activity and the elevating symptoms. The barium titanate based piezoelectric sensors is crucial in brain activity and elevating systems. They are crucial in neurostimulator based sensors because it detects the electrical activity in brain and nervous system. These sensors can detect even little changes in brain, allowing for the targeted stimulations of specific part of brain. The sensors shows the great sensitivity and precision. It allows them to become the most modest changes in brain activity, which is critical for effective therapy. The piezoelectric effect, or the capacity of certain material to create the electric charge in response to mechanical stress, underpins the operation of barium titanate based sensors. The electrical activity of brain applies mechanical force to neurostimulators, causing the barium titanate based piezoelectric sensors that generates the following characteristics. What we are studying, the 10th one, that are pacemakers. So okay, now we are discussing its uses. Barium titanate based sensors provide various advantages in pacemakers, and we have already discussed that. Yeah, that's the last one. And the piezoelectric effect, or the capacity of certain materials to create the electric charge in response to mechanical stress, underpins the operation of barium titanate based sensors in neurotransmitter. And the electrical activity of the brain implies mechanical force to neurotransmitter, causing the barium titanate based piezoelectric sensor that generate an electric charge. The neurotransmitter then measure and analyze this electric charge to find the most optimal stimulation parameters. The use of barium titanate based piezoelectric sensors in neurotransmitter provides various benefits. These benefits include decreased symptoms, a lower risk of complications, and a higher quality of life. Furthermore, barium titanate based piezoelectric materials can aid to lower the likelihood of devices malfunctions, which also improving the overall neurostimulator efficiency. Wearable sensor enabled devices. Wearable sensor enabled devices are mostly used to track information in real time, such as monitoring health matrices, predicting crises, and then a sensor is an input device that outputs the signal respect to physical quantity and provide an input. In other words, sensors may transition from energy domain to electrical domain, and the sensors is able to convert electric field potential and charges into electric signal. The applicant's criteria will be based on the wearable gadgets like fitness trackers, smartwatches, and increased using barium titanate based piezoelectric sensors to detect the physiological parameter like heart rate and blood pressure. Wearable gadgets have gained popularity in recent years because they allow the people to measure their physical activity, sleep habits, and other health parameters in real time. The barium titanate based piezoelectric sensor is crucial in wearable devices because it detects the mechanical stress induced by physiological signal like heart rate and blood pressure. These sensors can detect even a little change in physiological signal, enabling for precise and dependable monitoring of health parameters. The sensor's great sensitivity and precision allow it to detect even the most minor changes in physiological data, which is critical for efficient health monitoring. The piezoelectric effect, which allows a certain materials to create an electric charge in response to mechanical stress, underpins the operation of barium titanate based piezoelectric sensor in wearable devices. In case of wearable devices, physiological signals such as heart rate, blood pressure apply mechanical stress to the barium titanate based piezoelectric sensor, causing the electric charge to be generated. The wearable gadgets then measure the analysis the electric charge in order to track health parameters. The use of barium titanate based piezoelectric sensor in wearable devices provide various advantages for consumers. These advantages include precise and dependable health measure tracking, real-time physiological signal monitoring, and individualized health and wellness insights. Furthermore, barium titanate based piezoelectric sensors can assist to lower the risk of device failure and enhance the overall performance of wearables. Finally, wearable gadgets rely heavily on barium titanate based piezoelectric sensors to detect physiological parameters such as heart rate and blood pressure. These sensors have various advantages including sensitivity, precision, and small construction. Users benefit from the usage of barium titanate based piezoelectric sensor in wearable devices, which includes precise and reliable health metric tracking, real-time physiological signal monitoring, and individualized insights into health and well-being. Now, what are the advantages of barium titanate based piezoelectric sensor? It has many advantages like high sensitivity, excellent accuracy, design and its compact power consumption is low, and high dependability and stability. And then we'll discuss the challenges. Now, what are its advantages? Why are they important? High sensitivity. Barium titanate based piezoelectric sensors are very sensitive, allowing them to detect even little changes in mechanical stress. This high sensitivity enables accurate and consistent readings, making barium titanate based piezoelectric sensors such as excellent choice for applications that need precise measurement. The sensor's great sensitivity allows them to detect slight change in physical parameter, enabling real-time monitoring and control. Now, what is excellent accuracy? Barium titanate based piezoelectric sensors are intended to give the greater precision, which is critical in applications like medical devices and industrial automation. The sensors' great precision allows them to detect minute changes in physiological characteristics, enabling accurate measurement and control. Barium titanate based electric sensors can provide precise readings in a variety of temperature and condition. Now its compact design. Barium titanate based piezoelectric sensors have a small form, making them excellent for use in areas where the space is restricted. These sensors are designed to small and lightweight, allowing for sample integration into a variety of devices and systems. Barium titanate based piezoelectric sensors, small size makes them suitable for use in wearable device and other portable applications. Now its low power consumption. Barium titanate based piezoelectric sensors consume less power, making them ideal for use in battery powered devices, other applications where power consumption is a problem. The sensor's low power consumption makes them suitable for usage in application with restricted power, and the barium titanate based piezoelectric sensors are intended to operate at lower power levels, making them excellent for use in energy sufficient systems. Now we'll study the high dependability and stability. Barium titanate based piezoelectric sensors are very dependable and stable, making them ideal for use in applications requiring accuracy and precision. These sensors are built to withstand a wide range of temperature and conditions. They assure the dependable performance in variety of applications, and the great reliability and stability of barium titanate based piezoelectric sensor make them suitable for use in safety critical applications where failure is not an option. Challenges and its upcoming directions. Biocompatibility and toxic concern. That is, of course, a big challenge. Barium titanate based piezoelectric sensors offers a significant potential in variety of medical applications, including implantable and wearable sensors. However, one of the most significant issues with these sensors is their biocompatibility and toxicity. Biocompatibility refers to the material's capacity to interact with the live tissues cell without triggering unwanted effects. Some investigators have indicated that barium titanate, the substance used in barium titanate based piezoelectric sensor, is biocompatible. However, the biocompatibility of barium titanate based sensor can be influenced by the number of parameters including manufacturing process, surface roughness, and the presence of impurities. Toxicity problems are also a significant issue with the barium titanate based piezoelectric sensor. Barium titanate based piezoelectric sensors has been demonstrated the hazardous at large quantities, and release of barium ions from the sensor can produce a negative response in the body. Now, to address the biocompatibility and toxicity issues, researchers are investigating a variety of solutions, including surface modifications, its coating, or use of biocompatible materials. Now, surface modifications entails the altering the surface of barium titanate based sensor to increase the biocompatibility. What is coating? That is the process of placing a thin coating of biocompatible material on the sensor's surface. This can assist to lower the sensor's toxicity while also improving the biocompatibility and research. Now we will see that its future directions. In future, the research will need to work on producing barium titanate based piezoelectric sensors that are both biocompatible and non-toxic. This may be accomplished by employing modern manufacturing process such as 3D printing to construct sensors with geometries. Now the other issue is scalability. Scalability is the key difficulty for barium titanate based piezoelectric sensors. As the demand for these sensors grows, producers must ramp up manufacturing to satisfy it. However, scaling up manufacturing of barium titanate based sensors might be difficult due to the variety of factors. To begin, the production of barium titanate based sensors is complicated and necessitates specialized equipment. Scaling up production necessitates major investment in equipment and manpower, which may be challenge for enterprises. Second, the raw ingredients such as the barium titanate can be expensive, particularly when manufactured in big quantities. This might make it difficult for enterprise to remain profitable while increasing output. Now the other is cost effectiveness issue. In addition to the scaling issue, barium titanate based sensors suffer cost effectiveness concerns. The high cost of raw material, fabrication equipment, and labor might make it difficult for the manufacturers to create these sensors at reasonable price. Furthermore, the complicated fabrication process and the requirement for the specialist equipment might increase the production costs, ensuring the uniformity and quality control throughout the production can significantly increase the cost. How we can overcome this problem? To overcome these problems, manufacturers are looking at novel fabrication process like 3D printing or solder processing, which may lower the manufacturing cost and increase scalability. Researchers are looking at novel materials and material combination that might lower the cost of basic resources. Now, what are its possible futures? Possible future directions. In the future, researchers and manufacturers must work on the creating scalable and cost-effective production and procedures for barium titanate based piezoelectric sensor. And this may be accomplished by investigating R&D, working with industry partners, and experimenting with novel materials and fabrication processes. Furthermore, the creation of standardized fabrication method, quality control procedure can aid in consistency and quality control of large scalable manufacturing. In conclusion, scalability, cost effectiveness are significant hurdles for barium titanate based piezoelectric sensor. Addressing this problem will necessitate the development of novel manufacturing process, material and quality control system. Further research will concentrate on creating scalable and cost-effective technologies for manufacturing barium titanate based piezoelectric sensor. Now, integration with artificial intelligence. Integration with the artificial intelligence. It means that the barium titanate based piezoelectric sensors with the artificial intelligence technologies can considerably increase their performance. AI can improve the performance of these sensors by allowing for real-time data processing, pattern identifications, and decision making. One of the difficulties in integrating barium titanate based piezoelectric sensor with AI is the requirement for standardized data, format, and communication protocols. AI algorithm requires a huge quantity of data to learn and make choices. Barium titanate based piezoelectric sensor must be able to supply this data in an AI compatible manner. Another problem is the requirement of improved signal processing techniques to extract useful information from the sensor data. Now, barium titanate based piezoelectric sensors may create a massive volume of data which AI algorithm must be able to interpret in real time in order to make judgments. Now, integration with the Internet of Things like IoT. Integration or integrating the barium titanate based piezoelectric sensor with the Internet of Things technology can be advantageous. IoT connects the physical devices to the internet, allowing real time data transfer and analysis. One of the issues in integrating the barium titanate based piezoelectric sensor with IoT is ensuring safe and reliable data transfer. Barium titanate based piezoelectric sensors can create sensitive data which IoT system must securely communicate to avoid unwanted access. Another problem is the demand for low power usage and energy harvesting. A barium titanate based piezoelectric sensor can be driven by the energy and harvesting techniques such as vibration or thermal energy, but IoT system must be able to properly regulate the power consumption in order to operate reliability. In the future, researchers and developers must work on creating the standardized data formats and communication protocols for integrating barium titanate based piezoelectric sensor with AI and IoT technologies. To extract the relevant information from the sensor data, a complex signal processing technique will be required, and as will secure and reliable data transfer protocol to avoid access that is illegal. The widespread usage of barium titanate based piezoelectric sensor in IoT application will need the development of lower power consumption and energy harvesting technologies. Finally, the combining barium titanate based piezoelectric sensor with AI and IoT technologies has the potential to enable the advanced application in sectors such as healthcare, industrial automation, small cities. However, other difficulties must be addressed, including standardized data format, enhanced signal processing, safe data transport, and lower power consumption. So, now we will conclude that all the topic. To summarize, barium titanate based piezoelectric sensor has proven to be indispensable in medical devices manufacturers due to their remarkable piezoelectric characteristic, biocompatibility and mechanical durability. The sensors are used in variety of applications including diagnostic devices and real-time monitoring system. The material's distinct chemistry, which includes the alteration with dopants and nanostructure, has improved its performance, making it suited for the application in medical healthcare or modern healthcare technology. Ongoing research is likely to expand the possibility of barium titanate, notably in terms of downsizing, flexibility, and integration into wearable implantable devices. As the demand for non invasive, accurate diagnostic tools and patient monitoring solutions grows, piezoelectric sensors will play an important part in determining the future of healthcare. In conclusion, barium titanate based uh, piezoelectric sensors show a great promise for developing medical technologies. Their ongoing development is projected to result in more innovative, efficient, and patient-friendly medical device, hence increasing the care quality and outcomes. So that's all from my side. Thank you so much for hearing.